So let's try and understand what are the impacts of a poor first phase margin is, right? So this will be a kind of bunch of facts that we can use as a thumb rules for our design. Okay. So what does phase margin equal to 0 mean? So let's say I have a system like this. Right. Before we go into phase margin, can you tell me what is the loop gain? How will you evaluate loop gain? For to evaluate loop gain, I can simply desensitize the input, break the loop somewhere. So let's say I break the loop here, apply a test voltage V test, and observe this voltage V return. So what is V return? Is equal to minus A of S by K times V test. So loop gain L of S is A of S by K. Right? Okay, great. So now let's go back to whatever we were planning to discuss. So let's say this is this. Okay. Uh, and we found out loop gain, and we found out, let's say, phase margin. Somehow we have found out phase margin. So let's say uh, we have this is case of, let's say, phase margin, and this is, let's say, V naught. And the test that we are doing is we assume that the input Vi is the step input with respect to time, right? This is 0, this is some unit step, right? So that's ut incrementally. In the incremental domain, this is the unit step. Okay. So what do you think is going to happen if phase margin is 0 degree? What will V naught look like? So note that if phase margin is 0 degree means what? Phase margin is 0 degree means we are cutting that -10 point in the Nyquist plot, or in other words, we at unity gain frequency, the phase is -180 degree, or in other words, phase L of j omega is equal to -1. Exactly, 1 plus L of j omega is -1. 1 plus L of j omega u is exactly equal to 0. Right? That's what phase margin of 0 degree means, which means the system is an oscillator. Right? So ultimately, your system will oscillate, even though you have a step input. Right? So this is phase margin of 0 degree. This is what it will seem like. Right? So as it turns out, if you increase phase margin, right? If you increase margin, so let's say we go to from 0 degree to 30 degree. What's going to happen is, so let's say this is 1. I have given an unit step. So if I have given an unit step, what is the expectation? What is the expectation under steady state? If the gain, if the under steady state, if the loop gain is really high, if the loop gain is infinity, under steady state, what is the expectation? If the loop gain is infinity under steady state, this error voltage will be 0. So this voltage will be equal to Vi, which means this voltage will be a step. If this is Vi, V naught will be equal to kVi. This is the expectation at steady state, right? So that expectation at steady state is, in the plot of the output voltages, so I should see K times Vi, right? This is the expectation, I should see this. But as you can see in the plot that I showed in case of a 0 degree phase margin, and we have seen this with a couple of lectures back, that if you have L of j omega equal to -1, it doesn't matter what input you have given, even in the absence of an input, the output will oscillate, right? So let's say now we have a case in which phase margin is 30 degree, right? So in this case, clearly we are not encircling the -10 point, right? Which means the system is stable. But however, when you give an input as it turns a step input, as it turns out, the output doesn't settle abruptly. It goes something like this and eventually settles. It rings and rings and rings and eventually settles. And if you keep on increasing phase margin, and as it turns out, if you go to a phase margin of 76 degree, right, if you go to a phase margin of 76 degree, as it turns out, in a second order system, this is an important thing that I missed out. In a second order system, so your output will not ring and it will settle like this to an eventual value of k times pi. Okay. And if you keep on increasing phase margin beyond that, let's say now we go to 90 degree phase margin, then the output will kind of settle definitely, but it will settle even slowly. Okay. So this is essentially a lookup table kind of. Yeah, you can consider these type of plots as a lookup table plots with respect to what type of output you can expect if you give an input of a step, if you give a step input under different phase margin constraints, right, under different phase margin specifications. Okay. So clearly 0 degree is not good and 90 degree is very well, I mean quite stable, right, but sometimes it's neither possible to go to 90 degree, or definitely 0 degree is not possible. 0 degree we definitely don't want, so sometimes we settle in between. Sometimes we say that maybe 76 degrees is good enough, maybe 60 degrees is good enough. There will be slight amount of ringing, but the system will eventually settle. So that depends on the specifications that we are looking at. Okay, fine. So now let's take the example of a first order system. Let's say L of S is A naught by K 1 plus S by P, S by P1. So again, we do the Bode plot. So mod of L is single pole, so it goes like this, and obviously loop gain we expect to be much high, right, quite high, much greater than 1. So we obviously A naught over K has to be much greater than 1. This is an inherent assumption. And what will be the phase plot? The phase plot will start from 0. At P1 it will go to minus 45, and then reach minus 90 eventually, right? So what is so let's take an example. Let's say A naught over K is equal to 100, right? So this will be 100, and let's say P1 equal to 10 megahertz, 10 mega radian per second, not megahertz, mega radian per second, right? So let's say P1 is 10 mega radian per second. What do you think the omega UGB will be, or omega U will be? How do I find out? Same old, same old. What is the equation of this straight line? This equation of this straight line is A naught by K by S by P1, correct? And this, if I set to 1, so what do I get S to be? S becomes P1 times A naught over K, right? So in this case, what does it mean? P1 is 10 mega radian per second, A naught by K is 100, so this becomes omega U becomes 1000 mega radian per second. Okay, so what is the phase at the UGB? So the angle at omega U is what? Minus tan inverse omega U by P1, which is minus tan inverse 100, right? Now tan inverse 100 is as close to pi by 2, so this is almost equal to minus pi by 2. So what is our phase margin? Our phase margin is what? Pi by 2, right? Because we are pi by 2 away, additional phase away from getting to minus pi of total phase, right? So essentially phase margin is pi minus pi plus angle, which is minus pi by 2, or which is pi by 2. Right? So our system is stable. If I look at this take a look at this lookup table, so this corresponds to this plot, right? So the system will be unconditionally stable, first order system, not a problem. So now let's go to the second order system. Let's say L of S is A naught over K, 1 plus S by P1, 1 plus S by P2, right? And let's take another example of same, let's say A naught over K is 100, and let's say same P1 was at 10 megahertz, and let's say P2 is at 20 megahertz. P1 and P2 are close by, right? So let's say P1 is at 10 megahertz, P2 is at 20 megahertz. It goes like this. So, so let's figure out where is the UGB to start off, right? So step 1 is finding UGB. So let's assume the UGB is here between P1 and P2, right? If omega U is between P1 and P2, then what is the position of omega U? Omega U will be A naught by K times P1, which is 1000 mega radian. Sorry, this is mega radian per second, right? So clearly this is not, the solution doesn't match the assumption. So therefore, therefore omega U has to be greater than P2. So if omega U is greater than P2, what is the condition that I should apply? The condition will be it exists somewhere in this segment, and that will be A naught by K by S square by P1 P2 equal to 1, which means that if I put omega equal to S, mod of S equal to omega U, so omega U essentially becomes under root A naught by K P1 P2, which is how much? This is 100 times 20 times 10, that is 100 to 2, that is 140 megahertz, right? 140 mega radian per second, right? So this is 10, this is 20, this is 140, correct? So if that is 140, what will be the phase plot? What will the phase plot look like? So again, it will start off from 0 almost, and then it will hit minus P1, it will have some phase lag, it will hit minus P2, it will have some phase lag, and here it will also have some eventual phase. Okay, so what will be this phase? What will be this phase? This angle will be minus tan inverse omega U by P1 minus tan inverse omega U by P2, which is minus tan inverse 14, right, minus tan inverse 7, correct, which is how much? Which is almost close to, I think this is almost equal to 178 degree, right? I mean, it might be 178, 177, but it's very close to minus pi by minus pi, which means what? Which means its phase margin is PM is close to 2 degree. Okay, fine. So this is a poor system. This is a poor system. It will ring like crazy. So phase margin of 2 degree is not good. So if I have to fix this, then what should I do? If I have to increase the phase margin, let's say I want a phase, I want to ensure that the phase margin is at least 45 degree, right? Then what should I do? So what is the problem? The problem seems to be that by the time I am hitting the UGB, right, around the frequency of omega UGB, I've already have lot of phase lag, right? So I have to reduce the phase lag, right? So the solution is, so to improve phase margin, reduce phase lag, around UGB or around omega u. So how do I reduce phase lag? So what is the source of phase lag? Source of phase lag is a pole, correct? I mean, at least since we have not taken into zeros into account, the source of phase lag is a pole, which means that if I am closer to a pole, I will have more phase lag, correct? So I have to ensure that we are away from a pole. So clearly I cannot be, I mean, uh, so I have three segments, right? So if I am away from both P1 and P2, I have a problem. I cannot be here because, I mean, that is parallel to the x-axis, right? So I have to be between P1 and P2, right? So which essentially means that, which implies we need to ensure two poles below UGB are not close to each other, because if they are close to each other, they will give us more phase lag. If the poles are at higher frequency, if the poles are here, if the poles are somewhere, if the poles are somewhere here above UGB, their contribution will be minus tan inverse omega u by that pole, but that pole is at high frequency, which means they are giving relatively less phase lag, right? So low frequency pole gives high phase lag, high frequency pole gives low phase lag, right? So the reason is, low poles below UGB or poles near or below UGB, below omega u, causes more phase lags than poles above omega u, which are essentially high frequency poles, right? Okay, fine. So if that is the case, which means, let's say we are able to move, uh, let's say L of S is N naught over K by 1 plus S by P1, 1 plus S by P2. And let's say now, I mean, A naught over K, gain we don't want to compromise. So gain is 100. P1 let's say is at 10 megahertz and P2 let's say is at 200 megahertz, right? So what is the gain plot? What will it look like? So again, P1 something like this, something like this. Okay. So what will be by omega UGB? How do I figure out? So if the omega UGB is here, if omega u is between P1 and P2, if omega u is between P1 and P2, so omega u will be A naught over K times P1, which is equal to how much? 100 times 10, that is 1000, right? That is 1000 megaradian per second, right? So then also it's not possible, right? So even though we are, then also this assumption is not valid. So which implies omega u is ahead after P2, right? So essentially the omega u is still probably somewhere here. So we'll still have poor phase margin, right? So what is it? What is the next thing that I should try? I should try and ensure P2 is at even higher frequency. Let's say P2 is at 2000 megaradian per second, right? If P2 is at 2000 megaradian per second, or let's assume P2 is at 1000 megaradian per second, right? So that seems to be the break point. right? If P2 is at 1000 megaradian per second, what is omega u? So omega u by our calculations is, so omega u by our calculations was this 1000 megaradian per second, which means omega u lies on top of P2, right? Which means omega u lies on top of P2. So this is actually a quite interesting case, right? So this is 10 mega and this is 1000 mega, okay, and this is 100, okay. So what will be the phase? What will be the phase here? If P2 lies on top of UGB, the phase as far as the Bode approximation is concerned, this will be 0. Then I will reach minus pi by 4. Then this will go and then it will go something like this. So phase angle at omega u will be minus tan inverse 1000 by 10 minus tan inverse 1000 by 1000. So this, the first guy, the first term is minus tan inverse 100, which is for all practical purposes is minus pi by 2, and the second guy is minus tan inverse 1, which is minus pi by 4, right? So this is minus 3 pi by 4. So what is phase margin? Phase margin is 45 degree, pi by 4 or 45 degree, right? So if your phase margin is 45 degree, and if it's a two pole system, then what does it tell you? It tells you that the second pole of L of S, right? The second pole of the loop gain, not the closed loop gain, but second pole of the open loop gain, second pole of the loop gain lies on UGB, right? And if I have to increase the phase margin, this, so this in plain English means that this implies for 45 degree phase margin, P2 lies on omega u. And if I have to increase phase margin, so if we want to increase phase margin, where should P2 go? Should it go before omega u or after omega u? Clearly P2 should move above omega u, because P2 is giving us that excess phase lag. Note that the phase lag due to P1, since P1 is sufficiently away from omega u, the phase lag due to P1 is almost saturated at 90 degree, minus 90 degree, right? The phase lag due to P1 is saturated at minus 90 degree. P2 is giving me some hard one, right? So P2 is, in this case, the P2 is giving me 45 degree, and that's why I also have a 45 degree phase margin, right? If P2 gives me less than 45 degree phase lag, then I will have higher phase margin, correct? So which essentially means that if we want to increase phase margin, we must move the second pole, move P2 beyond omega u, right? So that is why very often you will hear circuit designers say that if for a well-behaved stable system, particularly if it's a second order system, since we expect the second pole to lie above UGB, right? So heuristically we try to ensure that when we plot the loop gain, we try to ensure that the slope of the loop gain around omega u is similar to the slope of a first order system, right? So if we only look at this slope, if we look only at this straight line, it seems like this is a first order roll off, right? This is a 20 dB per decade roll off. This is a minus 20 dB per decade roll off, right? So the rule of thumb is to ensure phase margin of greater than 45 degree, ensure uh, design such that design the loop design L of S such that around omega u L of S behaves like a first order system. Now note that this is not sacrosanct, right? So there are many assumptions that have gone into this. So one of the primary assumptions that I purposefully, I mean intentionally took without really making it explicit is we assume that all the poles of L of S are real, right? That need not necessarily be the case all the time, but most practical systems they are. This is the underlying assumption is all poles of L of S are real and no zeros exist, right? So these are some of the underlying assumptions, but as it turns out, these type of assumptions are more or less applicable in most circuits that we deal with, right? Okay, fine. So let's stop here. Uh, in the next lecture, which will be our last lecture for this course, we will see. We will take the structure of two-stage amplifier, right? Which is similar to that of an op amp, and we will see the implications of stability when we put that two-stage amplifier in negative feedback. Okay.